Do we have to implement like the computational graph in this iteration? Okay.
Get your name tag. Your name tag. Oh. Memorized your names yet?
Yeah, and you're fucking with your coffee.
Okay, all. You know the routine. Name tags out, laptops shut. We'll start in a minute. I need proper tense variables. Start on the dot at 8:35. Okay, we're going to continue with our series on how to train neural networks to emulate specific functions. So, Aditi, can you shut your laptop here? Here's how we posed it. We wanted the network to model some function, but you don't have the function. What you do have instead are input-output relations, pairs of instances where you have both the input, the x, and the corresponding desired output, d, for the network. So we start with a collection of such instances. And then what was the term that we actually wanted to minimize in order to train the network? Anybody remember? What was it? How did we define it? Anybody? Just the divergence? Pardon me? Okay, you have too many of you speaking at the same time. Pragya, maybe you can tell me. No, but what is it we actually wanted to minimize?
The difference between
Pardon me? Just the divergence? Was it the average or the expected divergence, right? So the network itself is modeling some function, and then you have the function that you want to model. There was a gap between the two. We shaded the area. We said we want to minimize this area, weighted, of course, by the probability of the specific x's. So that gave us the expected divergence. This is what we wanted to minimize. But the reason we are not minimizing the expected divergence is that you need the entire function. So instead of trying to minimize the error everywhere, so here's the function you want to minimize. Here's the function that your model currently captures, your network currently models. You want to minimize this area, but you can't actually compute it because you need, while you may have the network, you don't have the other function. So what we do instead is collect a bunch of training instances. And for each of these training instances, you have the error between what the network captures and what you want the network to capture. And so you minimize the average sum of all of those lengths. That is the average divergence. That is what we call the empirical risk. Now this, once I give you the collection of training instances, what is the one thing I can modify to change the lengths of those lines? The positions where I'm capturing them is given. what remains? The model parameters, that's all, right? So once I give you all of the training instances, the only thing that the resulting error is a function of is the set of model parameters itself. And so this is what? So we define our loss, which is the average divergence, so the average error, across all of the training samples. And this is what we will minimize. And we hope that if we can squish these errors down to 0 at all of these locations, the network function will end up modeling the function that we want. So we are going to be minimizing the empirical risk over all the training samples. This is empirical risk minimization, right? So, but it's also an instance of function minimization. It's an instance of optimization. You have a function, which is a function of the network parameters. It's also a function of the training instances, but once those are given, they cannot be modified, right? So the only thing that remains is the W. You can change the network parameters. And so now we have a case where we have a function that we must minimize with respect to its argument, which are the network parameters. And so we're going to spend a few minutes. Have a question?
Yeah, I was going to ask, why are we trying to reduce the empirical average divergence on the testing data instead of the training data?
That's not the testing data. Those are training samples, right? If you don't have the D on the test data.
But if that leaves us prone to overfitting if we try to minimize the loss as much as possible. Correct.
That's the only information you have, right? You're going to work with what you've got. You want the entire function, you just don't have it. So you're going to work with the samples. We've sampled it. The more you sample it, the better you expect to model the overall function, but that's about it, right? So now we're going to use derivatives extensively when we're trying to minimize a function. How do you define a derivative? Anybody remember, Peter?
I mean, like, you're just like, it's the change in y where you can change x.
Thank you, right? So that's about it. But actually, there's a little more to it, right? The way we define it is, when you speak of derivatives here, how you learned about derivatives in school is, if you're at any specific x, if you perturb the input by some delta x, the function value y changes too, right? And so we represent it as dy over dx. But the correct way to think about derivatives is that a derivative is this multiplicative factor alpha that you multiply the perturbation and the input by to get the corresponding perturbation in the output. We like to write this as dy over dx, but that notation doesn't really work. So what would be wrong with that notation? Anyone? Why does dy over dx not work all the time? Adam?
I don't know. Well, I was going to say, if you want it to be the number that you multiply dx by to get dy, that's not what you get.
Well, it is, right? The point is that you're making an implicit assumption over here that x is a scalar, right? But if x is a multivariate input, what is dx? Dx is also multivariate, right? Can you divide by a vector? No, right? dy by over dx is not a good notation. It doesn't generalize when the function is not a function of scalars. The only thing that generalizes when you think of it this way, delta y or dy is some alpha times dx. And so the alpha, this multiplicative factor, is your derivative. And we like to write d to point out that this increment must be really small, right? So when x and y are scalar, y equals f of x, then delta y is alpha delta x. I can represent this as dy over dx because I'm dividing one scalar by the other. And this is what we normally write. But we also like to write f prime of x. And why would I want to write f prime of x? Why is that a better notation? Yes?
You mentioned earlier the idea is that you can't divide by a vector, whereas like you can have like with f prime, like x can be a vector in that.
That's not really it. Even in the scalar case, f prime of x is a better notation. Why? Is this scaling factor alpha going to be the same for every value of x? So that alpha itself is a function of x, right? So f prime of x is a better notation because it tells you that the derivative itself depends on where you compute the derivative. This is important, right? And now, when I have a scalar function of a scalar argument, for functions of this kind, we are saying the derivative alpha is the scaling factor by which you multiply the perturbation of the input, right? So if dx is positive, for a positive increment of x, if this results in a positive increment of the function, what does it tell you about the function? Is it an increasing function or a decreasing function at that point? It's increasing. So the derivative is going to be positive, right? On the other hand, if an increment in x results in a decrement in y, then the derivative is going to be negative, and it's decreasing at that point. So you're going to have derivatives of this kind. Now, when your function is at a maximum or a minimum, then what is, and the function is continuous and smooth, what is the property we've learned about in school? A small increment, a tiny increment at that point is not going to change the function at all. So at those points, the derivative is going to be 0, right? So the derivative is 0 where the function is locally flat. This holds for scalar functions of scalar arguments, where the output is a scalar and the input is also a scalar. What when the input is a vector? So when the input is a vector, the same definition holds. How do I define a derivative at any particular point? So if x is a vector, I'm assuming column vector, it's going to be a vector of many components. What is the increment delta x going to be? Is that going to be a scalar? No, it's going to be a vector, right? What will the dimensionality of the increment be? The same as the input, right? And so if x is a vector, x1 through xt, delta x is also going to be a vector, delta x1 through delta xt, correct? And now if I perturb the input by a small amount, the output is going to change, right? And this is a scalar function, the output's a scalar, so it's a function of this kind. So a small change delta x is going to result in a small change delta y. What is the relationship between the two? For a small enough delta x, meaning the step is small enough, I can write delta y equals some alpha times delta x. Alpha is going to be the, what is the alpha here? The derivative, right? So just, so now, alpha is the derivative. What does alpha consist of? I have not asked that question yet. So now, what is alpha going to look like? Is it going to be a scalar number? Why not? So here, y is a scalar, right? So what's delta y going to be? Is this a scalar or a vector? Scalar, correct? And so delta x, what is delta x? It's a column vector, right? So what is alpha going to look like? What do I have to multiply a column vector by to get a scalar? A row vector, right? So your alpha is going to be alpha 1 through alpha d. As many components as the input itself. And now, if I actually write it out, you're going to get delta y equals alpha 1 times delta x1 plus alpha 2 times delta x2 and so on. Now there's something different between scalars and vectors. In the case of scalar, there's only one choice to make, which is, am I incrementing my x or am I decrementing my x? That's it, right? There's a delta x, it's a fixed term. In the case of a vector, how many different ways can I construct my delta x? It's infinite, right? Imagine just the case of 2 dimensions. So if this is x1 and this is x2, if you are over here, how many different directions can I step in? Pretty much anywhere. I could go this way, this way, this way, this way, this way, this way, this way. There's a choice, right? I can move in any, so the delta x can be anything. Now, there are 2 specific choices. If I move in this direction, then only x1 changes, but x2 does not. That's one specific choice. This relationship must also hold when I'm moving parallel to x1. So in that case, I'm going to find that delta x, this one is going to be delta x1 and a bunch of zeros, right? And so then delta y is going to be alpha 1 and a bunch of other terms. So this is simply going to be alpha 1 times delta x1 when I'm only perturbing x1 and not the rest of them. So this term that you get over here tells you the sensitivity of the function to a perturbation along x1. That's called the partial derivative of y with respect to x1. How does the function change when I keep everything else fixed and I only change x1? And so each one of those alphas is going to be a partial derivative along one of the directions. Everybody clear? Right? So now, this entire vector alpha is therefore going to be a vector of partial derivatives with respect to each of the components. Right? And it's going to be, what kind of a vector is it? Is it a column vector or a row vector? It's a row vector, right? Now, I can write that as a single vector notation. I'm going to use this inverted triangle notation. The inverted triangle is called the nabla. So it's nabla subscript x, y, which says that on the derivative, I'm taking the derivative of y with respect to the vector x. It's going to be a row vector. So if I write these things like so, of course, that thing is not coming back. We're left with only two boards. We said delta x1, delta x is a vector. It's a column vector, right? So delta y, so this nabla y, this derivative is going to be a row vector. This is an inner product, correct? What can you tell me about this guy? What does this vector of partial derivatives represent? We know it's a vector of partial derivatives, but what does it represent? Anybody know? Anyone? Yes?
The gradient?
It's the transpose of the gradient by definition, but what does it mean? Okay, so yeah.
Couldn't it be like related to our loss function? Because
So there's a physical meaning to it, right? Yes, James.
The direction of steepest incline.
The direction of steepest incline. And so why that is the case, by the way, the gradient is defined as the transpose of the derivative. The gradient has the same dimensionality as the input itself. Okay, that's the gradient. So the gradient is just a transpose of the vector of partial derivatives. Now here, that is an inner product, vector inner product. To understand what this means, let's look at the behavior of vector inner products. Consider this. Suppose I take some U transpose V. It's the inner product of U and V. So over there, the red line is my V. I can modify U. U can point in any direction for the same length, right? What happens as U rotates? When does this inner product become maximum? When the angle is 0, right? They're pointing the same way, right? And when they're pointing opposites, it's going to be the maximum, minimum, right? So you see what is happening over here. So going back to this guy, that's an inner product between the gradient and dx. The gradient is a property of the function, right? I can change dx. As we saw, the step can be in any direction. In which direction must the step be for this inner product to be maximum? The same as the gradient, correct? So going back over here, the red line is now going to be the derivative, correct? And to compute delta y is going to depend on the direction in which I'm taking a step delta x, if I fix the length of delta x. And this is going to be maximum when delta x is exactly in the direction of the gradient. So the gradient is the direction of fastest increase in the function. If I have a function of this kind, then at any point, the gradient is a direction along in the input space on x, and this is the direction in which we must, what's this? So this is the direction in which we must take a step in order for the function to increase fastest. There are many directions in which you can take a step for the function to increase. But the gradient where the function would increase, right? I could be taking a step slightly to the side or slightly to the side, that way and the function is going to increase. But the gradient is the direction in which this function is going to increase the fastest. If you walk in that direction, it's going to increase really steeply. And so if you walk exactly opposite to the gradient, conversely, the function is going to decrease fastest, right? Is that clear for everybody? Right. Okay. Questions at the back? Okay. Everybody, if you got it, raise your hands. I'm going to just check your hands. Who the heck is this? Yeah, if you got it, raise your hands. Anybody who isn't raising your hands, you're asleep. Okay, so, all right. We're going to use it. Now, at the minimum, the gradient is going to be a 0. It means that it doesn't matter which direction you walk in, the function does not change. There's another property. If I take a level set, if I slice the function at some height, then you're going to get a contour, right? That contour is a contour on the x-plane. And the gradient is always going to be orthogonal to this level set, to the contour. It's a property that we also use. Okay. There's another property of scalar functions of multivariate inputs called the Hessian, which is the equivalent of the second derivative. It's a matrix of second derivatives. It's the matrix equivalent of the second derivative of scalar functions. But anyway, just defining it. Here's a poll.
We don't use that.
Okay, you have 10 seconds, guys. 15. All right. So does anybody on Zoom want to take that first question? What is right? Someone on Zoom? A and B, right? Good. And what about the second question? Someone in this classroom? Which one's right? C? Sure enough, you're right. Okay, perfect. So now the problem of optimization. I've given you a function. Yeah? Pardon me? So the gradient is the transpose of the derivative. Remember how we defined it? Right? The gradient is in the same dimensionality as the input. The derivative is the multiplier. It's got to be the row vector, right? So here's the function. Here's a problem. We are given a function. We are trying to find the input at which the function is minimum. So this is the problem we're going to solve. In school, the way you learned it, you are given a function. You know the function has 0 derivative at the minimum. Well, oh, by the way, is this always true? Does the function have 0 derivative at the minimum? Can you give me an example where that's not the case? Pardon me? Well, but I'm speaking of, we're not saying it's not going to be 0 the maximum. We'll see more of this in a few minutes, okay? Later in class. Yeah, boundaries, Nirmal's right. Okay, so now here's how we we learned about derivatives, about function minimization. You found the location where the derivative was 0, but this could be either, actually, here's another poll. You're going to answer this question yourself. And you only get 30 seconds for this poll. This one's easy. Okay, stop here. Anyone want to take this question? Harvey? 3. Any? See, right? This is what we knew, right? Okay. What we know is that both maxima, now a minimum, a place where the derivative is 0, and which is where the function is a minimum or a maximum, is generally called a turning point. It's a turning point because the function turns over there. As you approach the function from any direction, it's going to flatten out and then it's going to start going the other way, right? At a maximum, it's going to first increase till you arrive at the maximum, then it goes down. At a minimum, it first decreases and then goes up. Both maxima and minima are turning points. We know this. So both maxima and minima have 0 derivative. If I plot the derivative of the function for both maxima and minima, at a maximum, the function is initially increasing, then it flattens, and then it's decreasing. So the derivative is initially going to be positive, then it becomes 0, and then it becomes negative, right? At a minimum, the function is initially decreasing, so the derivative is negative, then it flattens, it becomes 0, and then the derivative, the function begins to increase. The derivative becomes positive. So that's what the derivative is going to look like the red curve. It's going from increasing positive to negative at a maximum, from negative to positive at a minimum. And so if you plot the derivative of the derivative, the second curve, if you plot the derivative of the red curve, at a maximum, it's going from positive to negative, so that has its negative derivative. At a minimum, it's going from negative to positive, so it has a positive derivative. You look at the second derivative. If it's negative, it's a maximum. If it's positive, it's a minimum.
Someone on Zoom says we could have the second derivative 0.
Yeah, it can get arbitrarily more complex, but this is the general principle, right? So this is what we used to solve for minima. You found where the function had a 0 derivative, but then you checked the second derivative. If it was a negative, it was negative. You said it was a maximum. If it is positive, you call it a minimum. Easy, right? But then you can have all kinds of strange behaviors for a derivative. So for example, if you have a function like that f of x over there are 3 different locations where the function has 0 derivative. 2 of them are turning points. 1 of them is an inflection point. So if you look at the inflection there, then so all of these points where the derivative is 0 are called critical points. You can see if I plot the derivative is 0 at 3 different locations, but in the middle, the one in the middle is not really either a maximum or a minimum. It's one where the function was decreasing, slowed down, then continued decreasing, right? So what this means was the derivative was negative, then became 0, then went back to being negative, right? So the derivative is going to have this kind of shape you have seen in the middle of the curve. And then if I look at the second derivative, here's what you have. You're going to have negative derivative at the maximum, positive at the minimum. The second derivative in this case is actually going to be 0 at the inflection point. So things can get more complex. But for our purposes, it's kind of convenient to know that at maxima and minima, the derivative is going to be 0, right? Same thing with functions of multiple variables. The minimum is still going to be a turning point. It's a bowl around the minimum. And as you walk towards the minimum, regardless of which direction you walk in, the function is going to decrease, then it's going to slow down, then it's going to increase. So it's a turning point. And so what we really want to check for is a location where the entire derivative vector is 0. There is no direction in which you can walk where the function is going to change its behavior, right? If any of the components are non-zero, it means that's not a minimum. There's some direction in which you can walk to continue changing the function. So the optimum is a turning point. The gradient will be 0. The way we could solve for it is to just say I'm going to find where the derivative or its transpose are 0, right? But this is not going to be sufficient. Again, a maximum could also be have 0 derivatives. So then we check the second gradient, the Hessian. And the Hessian has some interesting properties, which we won't actually have a lot of time to get into in class, but it's on the slides in one of the later lectures. Let's say I have a function of this kind, which is a bowl, right? At this point, if I write the Hessian matrix is going to be symmetric. I can write out the eigenvectors of the Hessian matrix, right? Now, I can take any two directions, and if I walk, regardless of if I'm approaching it this way or this way, okay, I'm trying to draw in two directions at this point. The function is a maximum at this point, right? So this Hessian matrix is going to be a 2 cross 2 Hessian matrix. It will have two eigenvalues. Both of them will be positive. On the other hand, I can have a function of this kind. Think of does anybody have a sheet of paper? I'm going to use think of this, just imagine that this is a bowl, right? So then at this point, and let's imagine further that the bowl is bent down. So in that case, over here, if I came along this direction, that's going to be a minimum for the function. But if I came along this direction, that's actually going to be a maximum, correct? So in that case, if I looked at the eigenvalues of the Hessian, the eigenvectors are going to tell me the two directions which capture the most change. And the eigenvalue is going to tell me whether it's a maximum or a minimum. I'd find that in one direction, an eigenvalue is negative or positive, telling me that it's a minimum. In the other direction, the eigenvalue is going to be negative, telling me that it's a maximum, right? And so if I want a strict minimum where regardless of the direction in which, so just to give you an idea, if I have something like this, so something like, this, I'm trying to draw a board shape. I'm not being very successful at it, right? Then if I walk in this out here, if I walk in this direction, this is a minimum. But if I walk along this direction, it's a maximum, right? And so you'd have two eigenvalues. One of them is going to be negative and one of them is going to be positive. So if you want a strict minimum, then all of the eigenvalues of the Hessian must be positive. It says that regardless of which direction you're arriving at this location from, it's a minimum, okay? And so the test we would run is to check find out locations where the gradient is 0, and then check the eigenvalues of the Hessian at that point. If all the eigenvalues are positive, that's a minimum, you're happy, right? The problem is you need to have, what did I do? Something happened. Oh, can you? Wait, isn't Zoom sharing? Wait a minute, what did I do here? Okay, it came back, thank you. So the problem here is that closed form solutions may not always be possible, right? You won't be able to just solve the formulae and say, here's where the derivative is minimum, here's where the second, the Hessian has, and here are the eigenvalues of the Hessian. So it's not in Zoom? Uh-oh. Sorry, guys. Since nobody else is wearing it. Okay, back on Zoom? Yeah, it's the hat, right? It's a magic hat. I've got to keep wearing it. Anyways, so now when you have ugly functions of this kind, you can't actually just solve formulae and find where the minimum is. So we're going to take an iterative procedure. We're going to start from some initial guess like that x0. Then at that x0, you're going to look around and say, is this a minimum? If it's not a minimum, then you take a step. Then you get to the new position and say, is this a minimum? And then you keep doing this until you find the minimum. Now, how do you find that you've arrived at a minimum? The simple test is to say, is there any direction in which I can walk which would decrease the function? And if there's no direction in which I could walk, if I can, that would decrease the function, then this is probably a minimum, right? So, and now, in which direction do you step at any point? I'm at some location, and how do I check first if this is a minimum or not?
Gradient?
I can just check if the derivative is 0, right? Or check what happened, I didn't do anything. Okay, so I can just check if the derivative is 0, or if there's any direction in which I can walk, which would decrease the function, right? If there isn't, then that's possibly a minimum. Now, if it's not a minimum, then which direction would I take a step in? So here's what I can do, right? If I'm at some location, and if the function, I can check the derivatives. If the function has negative slope at that point, then would incrementing x reduce the function or increase it? It would reduce it, right? So if the function has negative slope, I take a step forward. If the function has positive slope, then would increasing x increase or decrease the function? Which direction do I step? Take a step backwards, right? So I'm going to just check the derivative. If the derivative is negative, the slope is negative, I take a step forward. If the slope is positive, I take a step backward from that point. And I keep repeating this process. So I can just write a little trivial iterative solution. At each point where I am, I just check the derivative, the sign of the derivative. And if it's negative, then I increment x by some step. Step is always positive here. If the sign of the derivative is positive, then I take a step back. I decrement by a step, right? I can compact this if clause into a single formula. And what I can do is to just say, I'm going to multiply my step by the sign of the derivative, and I'm going to go against it. So you can check. If the derivative is positive, this results in a backward step. If the derivative is negative, this results in a forward step, right? I can go one step further. Instead of checking there's also this issue, how big must this step be? And so instead of actually having some notion of a step size, I can actually make my step size proportional to the derivative itself. Now this formula is basically the same as the earlier one here. You're going to step forward if the slope is negative. You're going to step backward if the slope is positive. The amount by which you step is going to be proportional to the derivative itself, and it has this additional step size or learning rate parameter, right? We'll see why this kind of rule makes sense in a bit. So here's a little poll. Any questions? Ten seconds, guys. Yeah.
It's the same.
Showing the same thing as the one previously? Okay, then you know the answer, right? It doesn't matter. But here is the thing. At any location x, there may be many directions in which we can step. Something is off. Anyway, going back, you just got a minute of breathing room, that's all, breathing time. Here is the function, right? Yes?
Is it typically situation where you couldn't have a closed form derivative?
Yeah, if I give you an ugly function, then you can't solve for it, is what I said. In many cases, you won't even know the function, but that's a different thing. But even if I give you a function, you can't just say, here's the derivative, equate it to 0 and solve for it. So anyway, here's where we are. Suppose you're trying to minimize this function. Then let's say you're in that current estimate for the minimum is at the dot down here, which corresponds to the red dot on the function. Now this is not a minimum, right? Which direction do you want to walk in, move that perturb it in to head towards the minimum? you want to move in any direction which decreases the function, right? Which one, so of all the directions that you can take, which one is the one that you were most likely to choose? You want to go down the direction that reduces the function fastest, right? You're going to take a step negative, opposite the gradient. And so this is why we get this so-called gradient descent rule. At each location, at your current estimate, you compute the gradient, and then you take a step opposite the gradient. If you want to decrease the function, you take a step in the direction of the gradient if you want to increase the function. And that's because the gradient is the direction of steepest increase, right? Everybody with me? Okay. And the step size, there are many solutions to it, we'll deal with it later. When do you stop? You can keep checking your gradient, and you keep taking steps until the gradient is 0. There are many reasons why this is not a good strategy. So a better strategy is to say, you know, there was my function value before I took a step, and then I took a step, and the function value has changed. How big is this change? If you arrive at some point where taking any additional steps isn't really decreasing your function, then you're probably at a value you're done. So that's a better strategy. That's what we will use, right? So here's the overall gradient descent algorithm. You're going to start off with some initial, if you want to minimize a function with respect to f of x with respect to x, you start off with an initial guess x0. Then you iteratively take a step against the gradient until steps no longer decrease the function considerably, right? Everyone with me? Any questions? No. Okay. Now, why does it make sense for the gradient itself, for the steps, to be proportional to the size of the, to the magnitude of the gradient? Now, here are two different functions. For nice bowl-shaped functions, this procedure is going to arrive at a bowl. For functions like the one in the middle, you're going to arrive at some location where the derivative is 0, and that may not even be a minimum. That's one. And here's the other thing that we're going to get back to repeatedly. The best kind of functions are these. Here, you're far away, right? At this point, do you want to take a big step or a small step? Okay, how is the derivative high or low? High, right? So at these points, you want to take large steps. When you're here, very close to it, do you want to take small steps or large steps? You want to get there carefully. Is the derivative small or large? Small, right? This is why you want to actually have the step be proportional to the derivative. Okay? And here is a poll. This, I think, is an honest poll. You're going to get 30 seconds for it. Okay, I'll stop here. Anyone on Zoom want to take this question? Right, all of you are right. So you always want to take a step exactly opposite to the direction of the gradient, correct? This was supposed to be the previous poll. I just got mixed up. Now, returning to our problem. Here was our problem. That was just, you know, a detour into function optimization. What we want to do is to train the neural network. It's a function of network parameters. And it's an ugly function of network parameters. If I give you a network with 1 million neurons and a billion connections, W is a billion parameter term, right? We have no idea what this loss function looks like. You can't get closed form formulae even for the derivative, let alone equate it to 0 and solve for it. So what is the obvious approach we're going to take? Use gradient descent. We start off with some initial estimate for our parameters, and then at each point, so long as we can compute the derivative, the gradient of the loss with respect to the network parameters, you're going to keep walking against the gradient. Now observe over there, I've written nabla loss transpose. Why am I doing that? Why do I have the transpose? Shikhar, why do I have the transpose? Oh man.
Gradient is the transpose.
The gradient is the transpose of the derivative, right? The derivative is going to be a row vector. The gradient is going to be its transpose. That's why we have to be very clear, very careful about dimensions when you write these things down. Otherwise, you're going to get mixed up and you're going to find errors, okay? First, before I proceed with that, I'm going to have to set the problem up. Here is the problem setup. You're given a bunch of training pairs, input-output pairs. You have to minimize the loss function with respect to W. There are a whole bunch of things I have to define to make this tractable. What are all the things that you can identify that I need to define? Anyone? What are these things? I'm speaking of playing a game. How did that become a collection of numbers, right? I'm speaking of predicting a game strategy. How did that become a number? So I have to define my input-output pairs. Anything else I have to define? What is the function and what are its parameters, correct? That's an ugly function. And what is the divergence? These are all things I have to define, right? So let's start off with the simplest one. What is the function? This we know. This is easy. We are going to assume that is a neural network. It's a multi-layer perceptron. We're going to assume it's directed with a set of inputs and outputs. Information flows from the input to the output. There are no loops. Nothing comes back. Okay. And the parameters of the function are the parameters of this network. Easy. We're going to assume a layered network, meaning well, all networks are layered. So this is kind of a redundant statement because as we saw, we can always define layers. But what I mean specifically over here is that all of the neurons in the output have the same depth with respect to the input. It's always possible to draw a network where some neurons are deeper than some output neurons are deeper than the other output neurons. Those are ugly functions and kind of painful to deal with. We're going to assume that we have a structure where the output depth is all output neurons are the same depth with respect to the input, so it makes the computation a lot more structured. There's the input. The input is often called an input layer. It doesn't mean that there are any neurons over there. That's where you provide the input. This is just terminology. It's the 0th layer, also called the input layer. The layer where we get the outputs is called the output layer, and all the intermediate neurons are going to be called hidden layers. Now, we're going to further assume that the individual neurons have this perceptron-like structure, that they first compute an affine function of their inputs, and then the resulting affine value, which we represent by the symbol Z, that's going to be put through an activation function. And we're going to assume that this activation function is differentiable, right? So, and the parameters now are going to be the weights and biases. Now, the activation function, we're going to be generally assuming this kind of perceptron, but more generally, any differentiable function of the inputs is useful as a neuron in this network. And to answer the question, the 1 represents the bias over here, right? Now, what do these activations look like? We've seen the sigmoid activation, the one on top, and you can see what its derivative will look like. The derivative is initially going to be 0, then it's going to increase, then it's going to decrease again, and because the derivative is always positive, right? And then becomes 0 again. So now look at the sigmoid. It's 1 over 1 plus e raised to minus z, right? So if z is a large negative number, what is e raised to minus z? If z is a large negative number, what is e raised to minus z? Infinity, right? So what is 1 over 1 plus infinity? 0. So that function is going to be 0 when z is a large negative number. When z is a large positive number, what is e raised to minus z? E raised to minus z is 0, right? So 1 over 1 plus 0 is 1. So for large positive z's, it's going to be 1, and it's going to vary smoothly somewhere in between the two. And if you actually work out the derivative, it's going to be f of z times 1 over 1 minus f of z. The tan h function is basically just the sigmoid but it's scaled to go have a range of 2 as opposed to 1 and centered. So that it goes around 0. So it goes from -1 to 1. The tan h and the sigmoid are identical functions, except one is scaled and shifted. So naturally, when you plot the derivative of the tan h, what do you expect to find? Pardon me?
Like a similar derivative.
It's going to look very much like a sigmoid with one difference. And what is that? The height is going to be twice as much, right? Because I've scaled it by 2. So the tan h, although the function looks different, it's going to go from 0 to 1 and back, whereas in the case of the sigmoid, actually 0 to, is it 1? Yeah, and back. And whereas in the case of the sigmoid, I think it's going to go from 0 to 0.5 and back. I think, or 0.25. Anyway, then you have these other activations. The rectified linear unit, which is shown by the red line, the derivative is 0 on the negative side, it's 1 on the positive side. And when the input is exactly 0, the derivative is undefined, but it turns out that you can use any value between 0 and 1 and it would work just fine. Then there's also the blue curve, which is the smooth version of the rectified linear unit, which is log of 1 plus e raised to x, which has its own derivatives. But these are all different activation functions that we can put into the perceptron. You also have, but these are activations where a single unit takes a bunch of inputs and produces a single output, right? So when I think of it this way, every neuron in a layer is going to have one activation of this kind. But we also have things that we would like to call vector activations, where the activation takes a whole collection of inputs and produces a whole collection of outputs. So you have y1 through yl being functions of x1 through xl and w, all of them at the same time. And we will see, so how does this differ from the other case? So let's take a case where I have 2 scalar activations and say I have 3 inputs. Then each of these guys is going to be connected like so to these two neurons, right? If I vary the weight of this connection, only this output is going to change. This guy will not change. Whereas if I have a vector activation where I have 3 inputs going in and 2 inputs coming out, right? So maybe I'd have something like this. If I vary this weight, both of the outputs will change, are likely to change. So perturbing one input can change all the outputs in this case, whereas here perturbing an input is going to change just the corresponding output. Here's a specific example of a vector activation, a softmax, which you're going to use all over the place. The softmax takes these inputs z1 through zl and outputs y1 through yl. Now again, going back, if you look at your standard scalar activation, you have all of these things coming in. There's a z being computed and a y going out. And then there's a z being computed for the second neuron and a corresponding y comes out. If I vary this z, this guy is not going to change, right? If I vary this z, this guy won't change. Over here, observe something. It's e raised to z. For each output, it's going to be e raised to the corresponding z divided by the sum of the exponentiations of all of the z's. So if I increase any specific z, what's going to happen to the corresponding output y? Because e raised to z, if z increases, e raised to z increases, so the corresponding y will increase, correct? But then what can you tell me about the sum of all the y's? The sum of all the y's is 1, correct? So if any one of them increases, what has to happen to the rest of them? They have to decrease. So if I increment a z, the corresponding y will increase, but what about the other y's? They're going to decrease. Changing one y, z is going to change all of the y's, right? Now this has, so this is what we call a vector activation. It can be used anywhere in the network. We typically use it in an output. But we will see other networks where they're used all over the place. And now this has a nice property. E raised to z, is that ever going to be negative? Is e raised to z ever going to be negative? No, right? And the sum of all of the outputs is positive, correct? So this means that this looks like a probability distribution where you have a bunch of positive numbers that all sum to 1. So the softmax function produces outputs which look like a probability distribution, right? Now, in a typical network, I can also think of this guy as a vector activation, hide it all in a box, and this is going to be a special case where perturbing an input only perturbs the corresponding output and not the others. So this is also a perspective we can take. We've defined the function. That's the easiest bit, right? Now, the next thing to define are these input-output pairs. What are these input-output pairs? For the input, so there are 3 different things we have to define. We have to define the input. We have to define the output of the network, but we also have to define the target output because the network is trying to emulate something, correct? So, and the 3 are going to be very different. X is the input to the network. Y is the output of the network, and D is the desired output of the network in response to any input. If the network has, say, 10 outputs, what about the desired output? How many components will it have? Okay, the classroom is sleeping. Somebody on Zoom, 10, thank you. They're putting you to shame, guys. You're here. Answer me, okay? So that's what we're going to have. Now, let's look at this. The input is just a vector of numbers. Anytime you're feeding something to a mathematical object, it has to be numbers. So your input has to be a collection of numbers. It could be a bunch of pixel values for an image. For speech, it could be using a vector of features derived from speech. For text, you're going to be converting the text to a collection of real valued numbers. We'll see how later in class, but it's always going to be a collection of real valued numbers. The output, if the desired output is real valued, for example, if your network is performing a regression, then there's no big deal. If you're trying to predict a single scalar value, then the network is going to have a single output neuron, which outputs a real value, and the desired output is also going to be a real value. If your network is making a prediction of vectors, then there will be as many output neurons as the number of components in the vector you're trying to predict. The network output will be a real valued vector. The desired output is also a real valued vector. And because everything is real valued, there is no mystery. On the other hand, if you're performing classification, let's say you're performing binary classification, you're looking at pictures of and deciding, is this a cat or is this not a cat? In that case, you have to convert this question, is this a cat, to a number. So since there are 2 outputs, you're going to assign some numbers. The output will be 1 if it's a cat, 0 otherwise. And so it becomes a binary output. Now in this case, the network is making binary decisions, right? But here are 2 different things. First, because it's making a single binary decision, the network will have a single output neuron. The response to any input is going to be the desired output. I either present it with pictures of cats or pictures of objects that are not cats. So the desired output D is either going to be a 1 or a 0. But the actual network output is not going to be binary in this manner. And we saw why in the last class. Why is that? Anybody remember?
It's a universal approximator, but it's...
Yeah, but still, why did we want non-binary outputs? It gives you something that's not differentiable, right? You can't. So instead, what did we have? A sigmoid, which gave you a probability, right? So in this case, the network is going to have a sigmoid activation function, and the output is going to be that curve over there, which gives you the probability of the class. So you see there are P of y equals 1 given x. There are 3 different things here. The input is unique. The desired and actual outputs can be different, right? Yeah.
Is it recommended to do a softmax with 2 output neurons, or rather sigmoid is preferred?
They're going to be strictly equivalent. So that's at that point, it's just a computational thing, right? Now, suppose I have multi-class outputs. So suppose I'm still performing classification, but the network must decide if it's a cat, a dog, a camel, a hat, or a flower. Now, how do you convert cats, dogs, camels, hats, and flowers to numbers? The way you do it is you come up with a canonical order. You say maybe it's not quite alphabetical. Cat comes first, dog comes second, camel comes third, hat comes fourth, flower comes fifth. This is a canonical order that you decide on your own. And thereafter, every instance of cat is going to be a 5-component vector because there are 5 classes with a 1 in the position of the cat and 0 elsewhere. Every instance of a dog is going to be a 5-component vector with a 1 in the position of the dog and 0 elsewhere, and so on for each of our classes. This is what is called a one-hot vector. It's one hot because only one of the outputs is hot, the rest are cold. This is a desired output. This is what, when I give it a picture of a cat, I want it to output a 1 in the first position and 0 in all the others, right? How many output neurons will this network have? 5, right? So the desired output is an n-dimensional one-hot vector. But what about the actual output? We are still going to use the same logic that we use for binary classification. We don't want it to just jump from 0 to 1. That's not going to be differentiable. That's where the softmax activation comes in. The softmax activation actually, oh man, gives you a probability distribution over the classes. And so here you're going to use a softmax activation, which gives you a probability for all of the classes, and which sum to 1. Okay, so the desired, which is this guy. So again, the desired output is binary. Every output is 1 or 0, and further constraint that only one of the outputs is going to be 1, the rest is going to be 0. The actual output is going to be a probability vector. And you can see why it matches. When things are perfect, the network must be absolutely certain that it's a cat. So it will give it a probability of 1 for cat and 0 for everything else. But more often than not, it's not going to be so sure. Okay. And so when we are setting things up, you'll be given a number of training data instances, images of digits, along with information about which digit the image represents. So for example, you could have data like this. Your task may be binary recognition. Is this the number is digit 0 or not? And or multi-class recognition, which is classification, which is what digit is this? And so for binary classification, your labels are going to be binary, 0 or 1. This is a 2. This is not a 2. For multi-class classification, you're actually going to inform which class it is. But then I have the 5, 2, 0, 2, 4, 2. Are those the actual values we wanted to output? What do you actually want it to output? Can somebody answer me, Pragya?
Softmax of 1 hot, like in the one.
What is the desired output?
Ideally the 1 hot, but
The desired output is going to be 1 hot, right? So although these are digits, the digits themselves are just classes. We don't care, right? If we want maybe, in this case, a 1 hot vector, so for the class digit 5, you want a 10-component desired output where the 5th output is 1 and the rest are 0, right? And you're going to be given many such positive and negative instances, and you train your network from it. So we've defined the inputs and the function and all components of the function. Here's the last bit, the divergence. And this divergence, our loss needs to be differentiable, right? For the loss to be differentiable, we wanted the activations of the neurons to be differentiable. We saw this earlier. But then the loss also must be differentiable, because the divergence must also be differentiable, because if the divergence is not differentiable, then the loss is not differentiable, right? So now if you're performing regression, then the desired output is just going to be a real valued vector. The network output is going to be a real valued vector. I can just define various error measures between vectors. They're all real valued vectors. The most typical one is the L2 divergence, which is half the Euclidean distance. Why this factor half? The factor half is a matter of convenience. The factor half is, if I define the divergence as half of, what is the Euclidean distance? Is the sum over all components of the square of the difference between the actual and desired outputs, right? And then when you take a derivative of that divergence with respect to any component yi, you can see that the 2 cancels out, and all you're left with is the error. And so this harkens back. So that's going to give me, for example, w equals w minus eta times y minus d. This ends up looking again like the old Rosenblatt rule, right? So it's kind of, that's where this comes in. And so the derivative of the divergence over here is going to be a vector where every component is simply the error between the input, the actual output, and the desired output. If you're performing classification, then we're going to use a different error metric. If you're performing binary classification, the desired output is either 0 or 1, right? The actual output is going to be the probability of 1, since you're using a sigmoid. And so when I have a desired output of 0 or 1, then I can say class label 0, class label 1. For positive instances, that's going to be my desired output, right? For negative instances, that's going to be my desired output. This too just looks like an extreme case of a probability distribution, does it not? That it's certain about one class and absolutely certain about the absence of other classes. So the output of the network is a probability. The desired output too is now a probability when viewed in this manner. And so the divergence that we will use is going to be the divergence between 2 probability distributions, okay? And specifically, we will use the Kullback-Leibler divergence. And the Kullback-Leibler divergence is given by this formula. In the binary classification, it's guys, the desired output is d, which is either 0 or 1, right? So it's going to be minus d times log y, minus of 1 minus d times log of 1 minus y. So let's look at what happens. If the desired output is a 1 and the actual output assigns probability 0 to the target class, right? If y is 0, what does this look like? If d is 1 and y is 0, what does this look like? It's minus of, if d is 1 and y is 0, it's minus of d log y, right? Log of 0 is minus infinity, right? Minus of minus infinity is infinity, correct? If d is 0 and y is 1, what does it look like? If d is 0, you get 1 minus, the first term goes away, the second term remains. So you get 1 minus d, right? And log of 1 minus y is right? Infinity, because y is 1, correct? But then you have the minus outs. So you end up with, once again, you end up with infinity, as you can see. So you're saying that if the desired and actual outputs are mismatched, this divergence is infinite. If d is 1 and y is 1, what does this look like? One minus d becomes 0, so the second term disappears. Log of 1 is 0, so the first term becomes 0, this becomes 0, correct? If d is 0 and y is 0, also becomes 0, right? And it's monotonic. So here you have this property. If the output is the same as the input, desired output, the divergence is 0. When the output and input are exactly mismatched, the divergence is infinite. Now, why does this make sense? Let's say I give you a picture of a cat, then the desired output is 1, right? And if the network outputs a 0, it says, I'm absolutely damn certain this is not a cat. How wrong is it? It's infinitely wrong, right? So that's why you want that to be infinite. Whenever it's completely certain about the wrong thing, it's infinitely wrong. That's why this makes sense, right? Now, when I take a derivative of this, when d is 1, the second term disappears. So the only thing that remains is minus d log y. The derivative is going, what is minus the derivative of minus d log y with respect to y? D is 1, right? So what's the derivative of minus log y? Minus 1 over y, right? Is this going to be positive or negative? Is y a positive number or a negative number? Can everybody just say loudly positive? Okay, wake up and say it again. Is it positive or negative? Positive. Thank you, right? So what is minus 1 over y? Does that mean it's asking, does that mean that you must increase y or decrease y to decrease the loss? When the y slope is negative, in which direction do you want to go? Forward. Do you want to increase or decrease y? Increase y, right? D is 1, y is, so it says increase y, and y is a probability, will cap at 1, right? So the slope automatically tells you that the correct thing to do is to increase y. When d is 0, the first term goes away, right? What is the derivative now? Someone, James, what's the derivative when d is 0?
1 divided by 1 minus y, which is positive.
When d is 0, the derivative is, again, it's on the slides for you. It's 1 over 1 minus y, correct? And is this asking you, is this going to be positive or negative? Right? So is it asking you to decrease or increase y? Decrease y. When it's positive, you want to take a step back. So which means that if it's not a cat and the network has some feeling that this might be a cat, it says no, decrease the probability. Right? Make sense? Right. So here's the thing. If I plot, why aren't we using the L2 divergence? I mean, over here too, d and y are both numbers, right? I could be using the L2 divergence. If I plot the L2 divergence, here's what happens. The Kullback-Leibler divergence is the blue curve. The L2 divergence is the red curve. The first case is when the desired output is 0. The second case is when the desired output is 1. You find that both divergences are minimum when the network output is the same as the desired output, right? But the L2 divergence is nice and shallow. If the network is 100% wrong, if it's a cat and the network is totally certain that it's not a cat, it's still going to not give you very much error, right? It's kind of wrong, that's it. Whereas the KL divergence is really, really punishes you. So that's why the KL divergence makes a lot more sense than L2. But then let's say the desired output is 1 and the network output is also 1. What is the slope? When y is 1, what is the slope if d is 1? Minus 1, right? Is it 0? No, but the output matches the input, the desired output, right? Similarly, when y is 0 and the desired output is 0, what is the slope? You're finding that at these corners, the slope is actually 1 or minus 1, right? So at the minimum, the slope is not 0, which is why simply checking for the slope is not enough, right? If you're trying to keep taking steps until the slope becomes 0, you're never going to stop. And so when y equals d, the derivative is not 0, even though the divergence is minimum at those locations, something to be aware of. When I have multi-class classification, the situation is much the same. I'm still going to define a Kullback-Leibler divergence. And the Kullback-Leibler divergence in this case is going to be the sum over all the classes of di, which is the desired output for the ith class, which can be either 0 or 1, times log of di over yi, right? Which is minus sum over all the classes of di log di minus sum over all the classes of di times log yi. The desired output is usually 1 hot, correct? When the desired output is 1 hot, how many of the d's are going to be non-zero? So which is the one output which is going to be non-zero? The correct class, correct? So what does that formula reduce to? It's just going to be minus of the log of the probability assigned to the correct class. Correct? And when the probability assigned to the correct class is 1, what does this value become? Minus 1? It's log of yc, right? It's going to become, so when what is it going to become? It's going to be 0. And if the probability computed for the correct class is 0 by the network, what is this becoming? Infinity, right? So it's non-negative. It's 0 when the desired and actual outputs are identical, and it's sort of related to the gap. So it makes sense. Furthermore, now when I take the derivative, if I take the derivative with respect to the output for any of the non-target classes, what is that derivative going to be? 0, because they don't figure, right? And the derivative with respect to the output for the target class? Minus of 1 over yc. And once again, you see that this is going to be negative, right? So what is it telling the network, the algorithm? Yc must be increased, right, for the loss to decrease. That making sense to everybody? Right. So, and the intuitions are very clear, right? So if I write down the derivative is going to be a vector which is zeros for all the components except for the target class, where it is -1 over the probability assigned to the target class. There's something strange over here, right? This derivative is only asking you to increase the probability for the target classes. But you also want to be decreasing the probabilities for the other guys. They are the wrong things. So how does this work? This works because you're dealing with probabilities. If you increase the one, the rest just have to decrease, right? And again, note that when y equals d, the derivative is not 0, even though the derivative is minimum when y equals d, and all the other properties hold. So going back to our problem setup, you're given our training set of input-output pairs. We're going to minimize the following loss function, and all of our terms have been defined. We have one last poll. Okay, 5 seconds, guys. I'll stop here. And I'm going to walk up to the back of the class and pick on some unfortunate person in class and ask them for the answer. Who wants to be the victim? If you don't raise your hand, I will choose you. Okay, go ahead.
The second and the third one, because we saw that it could be 0 in a normal, like just a cup or
Yeah. Absolutely, right? The second and the third are the correct ones, right? Questions, anybody?
Why is it large?
The gray, which one?
Option C, the third one.
Okay. The gradient, what does this look like here? The derivative has a very large magnitude at the minimum, right? In this case, the derivatives is 1 at the minimum. So it can actually have a pretty large magnitude if it's at the boundary. And so the story so far, we've seen neural networks are universal approximators. They are trained to approximate functions by adjusting their parameters to minimize the average divergence between their actual output and the desired output on some training instances. But this depends on the input-output samples from which the function is learned and the divergence. To train the network, several terms must be defined. The network itself, the manner in which inputs are represented as numbers, the manner in which outputs are represented as numbers, which is numeric vectors for real predictions, one-hot vectors for classification functions, and the divergence functions that computes the error between actual and desired outputs, the L2 for regression, and KL for classification. And once all of these are defined, we are in a position to perform gradient descent, except there's one final step. How do you compute the gradient? And we're going to deal with that in the next class. Yes, okay? So over here, right, in this case, that's basically what the function is at the boundary, right? So right here, the derivative over here, for example, is minus of 1 over y. Y is 1, so you're going to get a minus 1. It just happens at boundaries, the slope need not be 0. Any questions, anyone? On Zoom? Yeah. It actually works out. The KL divergence is very nice. It turns out that if you think of it in terms of